Hi, I'm Mike. Welcome back to the shop, also known as West National Brewing. In this video, I'm going to show you how I designed, built, and tested this 4-foot tube and shell counterflow Wort chiller. Basically, it's made out of PVC and copper, and I think it works pretty well. I'm probably going to be making some modifications to it, but I want to show you where I am at this point. I'm also going to provide some links to a couple of prototypes that I set up first before settling on this design, and I'll provide links to those in the description. So I hope you enjoy this, and I hope it inspires you to give a try in building your own Wort chiller. I marked each one of the caps ahead of time. It looks like the center of the O and the Charlotte pipe, and between the V and the C. So that's what I'm doing to drill through each one of these. All right, if you're going to use an 1.5-inch pipe for your shell, it's a good idea to leave about 1.5 inches on this side for the connection of the PVC tubing. You'll need a 2 3/8-inch stub here to go inside this cap and inside the T, and that will butt the ends up together. So 2 3/8 there, and then with a 5-foot tube on the inside, you need the shell, the length of the shell to be 47 1/4 inches, and that will allow for this T and the cap and 1.5 inches on the outside. So those are the dimensions to follow. All right, I got it assembled. It looks like I probably did my calculations a little bit wrong. I missed an inch somewhere. So a 47.5-inch long main shell pipe, which goes between the T's, will give you 48 inches between the inlet and the outlet. So we've got a 4-foot shell, essentially. So that'll give that plus the shell out, or the inlet and the outlet, and it'll give 2 1/4 inches on the copper nub. So you'll have more than sufficient area here to attach the hosing or the tubing on the end. So we've got a 4-foot cross flow shell with two flows in it, two paths. So that looks pretty good. Now I'm going to make up the second one, and then we'll put these all together. All right, so the key variables in the cooling rate of a counterflow chiller, as I understand it, is the cross-sectional area of the shell, the diameter, and the makeup of the material that the tube is using. So it's copper, so it has a pretty good coefficient of for temperatures, temperature transfer. Heats up, cools down fast. The other part is the length of the overall unit. So the longer the length and the interaction between the fluids, the more heat you can extract. And turbulence. A really smooth flow isn't as good as a turbulent flow going through the shell. Turbulent flows can extract more heat because basically you're turning the water over more, and more of the water comes in contact with the tube, and you don't end up setting up a boundary layer of where the water is not extracting throughout the entire volume of the water. So a couple of ways of doing that are to add circular things like copper wire around the tubes, or using like Brillo pads that take up volume within the tubing. So what I'm trying to do right now is first get a baseline, understand how I've not put any of those things in at this point, so it's just the tubing, and I'm going to see how well that runs. If it doesn't work, then I will make it more complicated and adding devices that will help increase the turbulence of the flow. So if I'm not going to make it more complicated unless I have to. So we'll see how the baseline run does here. Here's the test setup. I've got a boiling pot of water. I'm at 214 right now. I'm going to turn that off. I'll run the pump through tube and shell 1 and tube and shell 2. I've got water coming in, cold water coming in. It's about 80 degrees coming out of my well. And the hot wort will come in here, and the cold wort will come out of here. So pass 1, pass 2, pass 3, and pass 4. So 2 and 4 are in the bottom shell, and pass 1 and 3 are in the top shell. And this is in a counterflow direction. So let's get it started. Pump on. I got a little bit of air in the pump. It's going to take a little bit to It's not too bad. Definitely not room temperature. Well, that's not terrible. Showing about 100 degrees, maybe a little bit more. I'm not sure that this thermometer is 100% accurate. I'll pour the water back in to the kettle at the end. So I'm calling it at 110. Digital thermometer says 117. 116. So I'm probably off by about 5 degrees. So this test setup has, there is no turbulence at all built into the design. It is just the PVC pipe with the 2 tubes running on the inside. There's nothing inside the shell to make the water inside the shell to be turbulent, to grab more of the heat out of the system. So not bad. I think if I can increase the turbulence by putting some packing or something inside to mix up the water, I think I've got a pretty good design here. So that'll be my next test, to add the packings and see what type of improvement I can get. All right, lesson learned number 1. The outlet pipe needs to be lower than the cap. So what I need to do is bring a T not above the elbow, but put it below the elbow. So what I essentially end up doing is putting a T into here, and then basically have a straight a straight exit. So that should take care of that and make it easier to clean. The other thing is this loop here between, which pass is this? So this would be between pass 1, I think it's pass 1, let's see. No, it's the inner one, so between pass, let's see, whatever that one is. Anyways, the bottom loop, let's just call it that. The bottom loop needs to have some way to get the fluid out because it's stuck in there. So I need to put a T here with a a faucet or some sort of drain mechanism there. So those are the two things that I'm going to add. Also from the original layout, if you have a sharp eye, I actually had this up at the top with the water inlet, and I realized that was a problem, so I switched it. But still not enough. You got to be able to get the water out the lowest point.